This is the second video for section 1.8, and in this video we will do some examples of calculating the local linearization for a function at a given point. Now remember, the local linearization is just a fancy way of saying the equation of the tangent line. So let's let our function f of x be x cubed plus 4x squared plus x plus 13. What we'd like to do is find the local linearization at the point a equals 1. And again, we draw our function, here's the graph, and the local linearization at a equals 1 is the equation of the tangent line at a equals 1. And once we have that, we can use that to approximate nearby function values. So let's remember our formula for L of x. It is f prime of 1 times x minus 1 plus f of 1, and you should remind yourself where that formula came from. It's a fact that we will very soon be able to prove and compute quickly and easily, but for right now, just trust me when I say that the derivative of our function is 3x squared plus 8x plus 1. So that means that the value of f prime of 1 is 3 times 1 squared plus 8 times 1 plus 1, which equals 12. Now, in the equation for the local linearization, I also need f of 1. So f of 1, I plug 1 back into the original function. I have 1 cubed plus 4 times 1 squared plus 1 plus 13, and that gives me 19. So remember the interpretation, f prime of 1, which equals 12, is the slope of our local linearization, and 1 comma 19 is our point that the tangent line passes through. So I plug everything into the formula for L of x. I get 12 times x minus 1 plus 19, which simplifies to 12x plus 7. Now that I have a formula for the local linearization, I can use it to approximate the function value at 1.2. So what we say is that f of 1.2 is approximately equal to L of 1.2. And how do I calculate that? Well, that's easy. I just put 1.2 into my equation for L, and I guess I used the unsimplified version of L. So I have 12 times 1.2 minus 1 plus 19, which is 21.4, and you can confirm that. The actual function value, it turns out, is 21.69. And the question is L of x too big or too small? As we can see here, it's obviously too small, but we also could have answered that before because f is concave up at a equals 1. So the tangent line lies below the graph, so it's going to give us an approximation that is too small. Okay, so for the same function, find the local linearization at a equals minus 3, use it to approximate f of negative 3.1, and answer the question, is the approximation too big or too small? So what I recommend that you do is try this and then come back and watch my solution. The first thing you should ask yourself is, can I just use my previous local linearization to approximate f of negative 3.1? And the answer is a big fat no, absolutely not. You cannot do that. Why? Remember, the local linearization is local. It only works for points that are really close to 1. If we look at this graph, you see that the values that you get from plugging in numbers near 1 are not necessarily going to be valid approximations for points that you would get by plugging in values near negative 3. So we need to recalculate a local linearization at negative 3. So if we calculate the derivative at negative 3, we get 3 times negative 3 squared plus 8 times negative 3 plus 1, which is 4. And that tells me the slope of my local linearization. I calculate f of negative 3 by plugging everything into the function. And just by coincidence, I also get 19. So my conclusion is that negative 3 comma 19 is the point on my local linearization, the point on my tangent line. So my local linearization is 4 times x minus minus 3 plus 19, which simplifies to 4x plus 31. So if I use the local linearization to approximate f of negative 3.1, I put in negative 3.1 into the equation for L, and I get 4 times negative 3.1 plus 31, which is around 18.6. And I know that this approximation is going to be too large because at this point f is concave down, so the tangent line lies above the graph of the function. So this is too big of an estimate, and indeed, if you compute the actual value, you get something around 18.55. So indeed, the approximation is too large.